Welcome here. I'm very happy to be here at JFOL, and it's one of my favorite one-day conferences ever. So very happy to be here. My name is Oleg Šelajev, and I work as a developer advocate for project GraalVM at Oracle Labs. And today we're going to go talk about GraalVM, and we're going to look at this from the point of view of a normal developer. So mostly how you can start using that, maybe how you can benefit from it, and so on. If you have any questions, or if you want to follow up, or if you want to just chat with me about life, programming, software engineering, any questions about this session or GraalVM in general, you can find me on the internet. I go by @Šelajev almost exclusively. If not, you can Google it, and you will find me definitely. So Oracle Labs, if you don't know, is a research and development institution department within Oracle. So its main focus is to do proper academic science work, right? To push forward the boundaries of what we know as humanity about computer science, about software engineering, about how we can do computation, how we can do that more efficiently, better, faster, easier. And then after that, convert that accumulated knowledge into industrial products, right? Products for the ecosystem, for the community, hopefully for the benefit of the parent company as well. But first and foremost, it's about figuring out new things and finding new approaches to software. So before we start, please do not make any forward-going business decisions based on the contents of this presentation. That is very important. With that said and done, we're going to talk about GraalVM. One line that would describe GraalVM is that it's a high-performance, polyglot, embeddable virtual machine capable of writing programs in different languages. So currently it supports Java and JVM languages, so Kotlin, Scala, Groovy, Clojure, everything that compiles down to the Java bytecode. It supports JavaScript, including node.js applications. It includes support for R, for Python, for Ruby, and it also can run native languages through an LLVM backend. It's front-end for GraalVM, but for the languages, that's a backend. So there are a number of languages that we can run currently, and the premise is that you are able to run all of them efficiently, right? We want our software to be fast, and for that we need high-performance runtimes to run that software, right? Nobody wants slow programs. So GraalVM can do that, and not only just run individual programs in those languages, but also efficiently mix them together in a single program. So you can choose which components of your application are written in which languages. So if you have a good tool for a particular job, like machine learning in Python, then you can write Python for that. But if you want to use that in the context of a Java application, you can do that with GraalVM without the overhead for serializing data structures between those languages. If there is one takeaway slide, one picture that you'll remember out of this talk, I probably would like it to be this one. So because it illustrates what GraalVM is and what's its place in the ecosystem of different runtimes and languages. So on top, we have the languages that GraalVM supports, and the support for the languages doesn't require a huge amount of effort. It's non-trivial, of course. Very few things are very trivial. But you don't need to support a language. You don't need to write a complicated virtual machine and the runtime and the compiler to transform the programs in that language down to machine code yourself. But you need to specify an interpreter. And GraalVM will compile that at runtime, just in time. It will compile that to a very efficient machine code. And then it can run that in different environments. So it can run that in the context of the normal JVM on OpenJDK, or it can run that in the context of a Node application, and you will have the normal things that you would expect from Node, like signal handlers and the event loop. So all the code that would expect things from Node will be able to run that. And also, it's an embeddable machine. By design, it was created that you can build it into your applications. Java applications, if you have like a large platform that you want to enhance with ability to execute snippets of, say, JavaScript to allow customization. Or it could be a native application. In this mode, GraalVM is built into certain experimental builds of Oracle database, and you can download and experiment with that. And for example, you can write stored procedures and user-defined functions in JavaScript. Normally, you would do that using PL SQL, but if you feel more productive and more comfortable with JavaScript, you can do that now. The same way, there was a plugin for MySQL. I don't think it's currently publicly available, but we will get there. And you can run JavaScript and Python code inside MySQL in a database. If you, for example, want to do machine learning right where your data is, that's maybe a great opportunity. And also, the last but not least mode of running programs with GraalVM is creating standalone binary native images. So we can analyze your Java bytecode. We can statically compile that down to machine code. And then as a result, you will get a blob, right, like a single binary file that you can run in somewhere, in an empty Docker container or in your favorite Linux server. And that's very efficient. It's compiled ahead of time, so it starts really fast. It doesn't consume as much memory as normally you would expect from a Java program. And it's a very interesting mode. By default, if I would say that something runs or doesn't run on GraalVM, I personally would be talking about the default mode on the OpenJDK, so in the context of JVM, especially when talking to Java developers or people who are doing work in JVM languages. But there are differences, what languages exactly you can run in which contexts, and there are many things that you can do. So obviously, with that many components and different moving parts, it can do very many things. It's a versatile platform. So if you're interested, probably the best entry point into whatever it can do at all would be to read an article on the GraalVM team blog that we published back in April about 10 different things that GraalVM can do for you. And we're going to go through some of them today, and I'll maybe show a couple of demos. But if you are interested into getting a more comprehensive picture, you're welcome to read that. A surprising fact is that when we prepared this, and this was written by Chris Seaton, who is currently the lead for our Ruby implementation, when he compiled that list, even people on the GraalVM team were surprised that GraalVM can do some of those, which is fantastic. Which just means how versatile the platform is, and just gives me hope that eventually we're going to figure out at least like some parts of the use cases that it enables. But today we're going to talk mostly about GraalVM from the point of view of a Java developer, or, well, Scala developer, somebody working on the JVM. So let's talk about that. Infrastructure, how it works, what components are in there, because it's a large project. When you run programs, imagine that there is an underlying platform. And in our case, that would be the JVM. And that is a normal JVM. And when you download the binaries that we, GraalVM team provides, it comes with an, I think, OpenJDK or Oracle JDK binary, currently 1.8. And the main component of the GraalVM project is the Graal Compiler. So it's a compiler that is able to compile Java bytecode just in time or ahead of time into machine code. So it integrates with the JVM using JVM CI, which is the Java Virtual Machine Compiler interface. It's a thing that was added to OpenJDK, I think, in Java 9, and we backported that to Java 8. But it's an official interface. If you want to plug a third-party compiler to your JVM and you want to compile your bytecode yourself, this is what you would implement. This is how you implement a compiler for JVM. And through that interface, and with the existence of the Graal Compiler, GraalVM can run Java bytecode. So we can support all the JVM languages just with one layer on top of the default hotspot VM. Now, for other languages, you need a little bit more work because they do not compile natively by default to the Java bytecode. nor do we want to make them compile to bytecode, because that's hard work. So there is a layer called Truffle framework. Truffle framework is a framework, a library, to implement managed languages. It comes with an API that helps you to describe an interpreter for the language. So all you have to do to add support is to describe an interpreter that works on the abstract syntax tree of the language. So this is the first step that anyone would do when they create a language. They create an interpreter for that, right? So you can imagine there is a tree of operations, and then every node has children, and to evaluate a node, you evaluate children first, and then you perform the operation. And it's fairly straightforward to describe that using normal Java code, and all of the GraalVM project. Everything is written in Java. The compiler is written in Java. The Truffle framework is written in Java. And the interpreters for the languages are written in Java, which makes it very readable and maintainable to Java developers, which is very good. Because normally that would be written in native code, say C or C++. And that is, if you're a Java developer, if you have a lot of experience with Java programs, it is much harder for you to read and understand native programs, because it's just a different language. And then an important bit is, on the Truffle framework, we have the LLVM bitcode interpreter. So that allows us to run programs in native languages compiled to LLVM bitcode. So LLVM in itself is a compiler toolchain, right? So it's a project that was created to simplify development of the compilers for C, C++ native languages. So they introduced the internal representation, LLVM bitcode, kind of like JVM bytecode. So they compile the programs into that, optimize that, and then compile them to machine code. So GraalVM takes this bitcode, and it can interpret that, and at runtime, compile that interpreter very efficiently. If you ask how efficiently, and how efficiently can you run interpreters, because this is typically a very slow approach to running programs, you want to compile them, right? You want to strip all the unnecessary information. You want to specify and specialize your program to run for particular data and want it to be fast. Then it's pretty decently fast. The comparison with different languages is a little bit hard, but if we look at the range of industrial benchmark that are used for particular languages, then we get the results approximately like this. And this, you have to understand that this is the average temperature across the whole hospital of benchmarks, right? It doesn't necessarily paint the picture of what will happen to your code. GraalVM is a little bit faster on Java benchmark. It's kind of reasonably faster on Scala code. And most typically, it's because the C2, the compiler in the hotspot virtual machine, intimately is aware of the patterns that Java programs produce, the bytecode patterns. So it knows how to optimize those really, really well. So it's kind of hard to beat that. But Scala programs, or say Groovy programs, they produce a little bit different patterns of the bytecode when they compile. So C2 isn't as good at those, and there are more opportunities to be faster. So if we talk about dynamic languages, then GraalVM's approach is way, way faster, which is great, because faster is better. If we talk about native, surprisingly, it's just a little bit slower than native compilation. So it's not significantly slower, which is great result, because typically you would think if something has to be mission critical fast, it has to be written in native code, right? It has to be written in C or C++. But sometimes you don't want to do that, and you still want to get performance. So what GraalVM shows is that you can run interpreters at the speed comparable to native. And also our JavaScript implementation is sufficiently fast. It's a little bit slower than V8. Hopefully in the future, I can show a slide where it's slightly faster than V8, and then maybe faster than V8. But V8 is a really good virtual machine for running JavaScript. Specifically targets JavaScript. It's created, very many hours were put into making that really, really good virtual machine. So running on par with V8 is a great fit, especially if you consider that GraalVM offers a universal approach to running all languages. There are no specific optimizations for particular bits of JavaScript code. So it's fast. And if you want to know why it is fast and how it works under the hood, then probably the best source of information currently is this academic paper. So since we are at Oracle Labs and we are academic into academia a little bit, then the results are published in papers, conferences, journals. So you can read that. It's a little bit harder to read than your typical blog post on the internet, but it explains the information, the approach, what things the Truffle framework requires from the compiler, and how Graal Compiler actually provides those things occasionally, and so on. So if you want to dig deeper, this is a good place to start. But if you don't want to dig deeper and go full academia on that, you can look at the source code, for example. GraalVM is an open source project, so the source code is available on GitHub. You can go and you can click on the files, and they're Java files, and you can clone that and boot it up into your favorite IDE, and you can click around through the definitions and see what it does. You can build it yourself. If you don't want to build it yourself, then you can use builds that the GraalVM team provides you. So currently we have a community edition, which is the components, open source components available on GitHub, built into a single binary that you can download, a distribution binary. You can download that, you can run it. The licenses there for the components are normally the same that would be for the underlying platform. So Java stuff is, or Java-related things are licensed under GPL2 plus class pass exception, just like OpenJDK. Node components are under similar license to normal Node, Ruby to Ruby, R to R, and so on. Right? So we would like it to be a drop-in replacement for the runtime that you use for running programs like that. And for Java, for example, GraalVM distribution is a drop-in replacement. Currently, we publish the builds based on Java 8. Who uses Java 8 in production? Who uses something later than Java 8? 9 plus. Excellent, 4 people. Who uses something older than Java 8? 7 minus. Also 4 people. Cool, so we have a normal distribution with tiny tails on both sides. So Java 8, this is great, because for you, GraalVM distribution could be a drop-in replacement, right? Because it comes with Java 8. If you would like to have additional performance and some security and scalability features and run that in production, you can obtain Enterprise Edition of GraalVM. So currently, it's available for evaluation purposes. It sits on the Oracle Technology Network, so you can just go there, click that you read and accept the license, which is the typical OTN license. I think it's the same when you download Java and other products from there. And you can evaluate that. So it comes with a more sophisticated compiler, so it will produce better results performance-wise. And it comes with a couple of features which are critical, not critical, add value to production systems. But it's functionally equivalent to the Community Edition, or Community Edition is functionally equivalent. All programs that you run on Enterprise Edition, you can run in the Community Edition. So you can evaluate that, you can try that, you can use Polyglot apps and create native images and do all that, and then make a conscious choice if you want additional performance, and then inquiry how to obtain the Enterprise Edition if you want. I think currently you need to send an email. Yes, because there are no full product description for GraalVM yet. We are hoping to fix that in the future. But now you can evaluate that. So let's evaluate that. How many of you use Java? Mostly day-to-day. Excellent. All of you. This is great. I'm going to show you a demo that shows that GraalVM is indeed a high-performance virtual machine for Java. Let me first show you. So I have downloaded the GraalVM Enterprise Edition 1.0.0 RC8, the release candidate. We started releasing them back in April. kind of communicating to the community that we are ready to release 1.0 soon, and to encourage people to try and submit issues and ask for things that maybe are not done in the best way for the community. And we received quite a bit of feedback, and we've been doing those release candidates monthly since then. I think release candidate 9 came out this Monday, but I haven't updated yet. So if you look at the bin folder, right, of the GraalVM distribution, you can find the normal Java commands there that are similar to what you get in the OpenJDK. So you have Java, Java-C, Java-P, and so on. You have JJS. So normal stuff that comes with the OpenJDK. And you have other GraalVM specific things, like the JavaScript launcher, the LLVM interpreter, the native image utility for standalone apps, the Polyglot shell, and so on. Ruby. You don't get Ruby by default, but there is a Graal updater utility that you can use to download support for additional languages. So Ruby, R, and Python you have to install with a command, something like gu install Ruby. And it will download the source for the interpreter from GitHub, and it will install it in the thing. So with this, I can run Java minus version. You can see that it's normal Java. It's based on JDK 1.8.172. It comes with the JVM CI of certain version, and you can run normal Java commands. And this is what I will do. I have a benchmark here, a normal benchmark that uses some stream API, right? We all write Java 8 compatible code, so we would like to use the stream API because we want to be sometimes functional, and we want to stream values and then apply those small individual map functions to transform the data. And this is the code that you might find somewhere in a normal user application space, right? Probably it's not how you write low-level frameworks or some low-level math manipulations, but this is what typically developers would write. Maybe not with integers, unless you get salary for streaming an array of integers. But it's this code resembling normal code. So this benchmark is written using the JMH, the Java Micro Benchmark Harness, which is the default way to micro benchmark Java things. And it kind of helps us not to make obvious mistakes with benchmarking things. So it will prevent us from measuring completely incorrect thing, right? So it will not allow us to eliminate the dead code or do other tricks. It's a normal benchmark. The source code for that is available on GitHub, and you can run it yourself. So what I'm going to do, I'm going to run this benchmark without Graal first. So I'm going to use the Java command from the GraalVM distribution, and I will pass it the -use JVM CI compiler flag. So this will disable the JVM CI compiler. So it will run without any knowledge of Graal compiler. It will just run normal Java from the JVM, and it will run normal C2 compiler. So I will just run it here. Run, no Graal. Excellent. It runs. It will run for 40 seconds. What it does, it warms up our JIT. It runs the test methods under different loads. It ensures that it compiles. And you can see that it warms up and then discards that information and then does measurement for several iterations. The normal benchmark stuff. And you can see that typically on this particular machine, one iteration of this test method will take 178 nanoseconds per operation, which is a good result, right? JVM is a sophisticated state-of-the-art virtual machine. It's fast. The code is normal, right? So it should be fast. You can see the score is for 178 nanoseconds per operation. Now I will run the same thing, but with the Graal compiler. So I will not disable the Graal compiler. And by default, the Java from the GraalVM distribution comes with the Graal compiler enabled. So I will just run this now. Run sh. Nope, sh. Run sh. And I will run it with Graal. And I will not show you the numbers first, because I want this to be a surprise. So coming back, so it's a small benchmark, and of course, take the results of that benchmark with a grain of salt. But let's have a small vote here. Who thinks the result with Graal will be faster than normal Java? Okay, who thinks it will be slower or on par with the JVM? Why would I show you a benchmark where we are slower? No, it will be faster. Of course it will be faster. First, because it's a demo, and you can assume that it should be faster. But the question is, how much faster, right? So JVM is it's fast. And I showed you benchmarks where it's like 2% faster than JVM on average. Who thinks it will be 2% faster? Let's make an auction. Who thinks it will be 5% faster? OK, cool. 5% is decent. 10% faster? Very nice. Who can go higher? 20% faster. 50% faster. Who believes in Graal Compiler? OK, 50%. That's quite a bit, right? Like, it's not easy to beat JVM for 50%. Twice as fast. The very optimistic people. Let's see how far can you go. 5 times faster. 10 times faster? How ridiculous. OK, so the top bet was 5 times faster and 15 times faster. 10? OK, 10. Let's see the result. So we can see that one iteration of this method with Graal Compiler enabled boils down to 10 nanoseconds per operation. 180? 10. That's 18 times faster, more or less, roughly. That is ridiculous. Yeah, that's worse than applause. Thank you, Nikolai. So this is a small example. Like, if you run your programs on GraalVM, they won't be 18 times faster. That's just unreasonable. But what it shows you that on some pieces of code, Graal Compiler can do optimizations which are way better than normally you will get from C2. And while the result and the performance boost will vary based on your actual application, on your workload, there are snippets of code where it is ridiculously faster. And the thing is, there is nothing in Graal Compiler specific to this benchmark, right? It's just, it uses the high-level optimizations that it applies to all Java code, and it just runs this particular benchmark way, way faster, right? That's a good question, whether it's faster than native. So I think for this particular benchmark, it just optimizes that to like a value read, because I feel like 10 nanoseconds, you cannot do much more than read a couple of values. But it's not a specific optimization for this particular benchmark or for the idiom stream map reduce. It just, Graal Compiler comes with a really good inlining algorithm, the polymorphic inlining algorithm, where you have interfaces that fan into very different implementations, like collections API, or here you have stream API, and then different implementations on stream have different implementation of map methods. But Graal Compiler can optimize those things really well. And it comes with a very good escape analysis algorithm, which allows us to eliminate allocations of very many objects, auto-boxing and so on. So here, for example, it doesn't box to integers, big integers all the time. And because we don't need to do that, we can be much faster, right? So I think 3 optimizations contribute the most for this. So escape analysis, inlining, and polymorphic inlining. But it will also benefit other code patterns as well. There is a quick question.
Did you try with an in-stream?
Yes. That's a very good question. So let's not go into the API discussion, please. We tried it on a number of different benchmarks with arrays, right? Like on strings, we sorted out some and filtered objects like a person with height and hair color and some other attributes that you would maybe use in your system. Like you typically would work on objects rather than on integers. And we published some results on those benchmarks, and you can check it out. Typically, Graal Compiler will outperform the stock JVM about twice, maybe, 1 dot like 8 times. And then we run a Java Scrabble implementation, which is a Scrabble game, which just is written using stream APIs, the full game. And we run that in a benchmark in a loop and measured how fast this solves the Scrabble. And it also was something like twice as fast, which is great, because it means that if your code is using stream API, you can download a different virtual machine, a drop-in replacement, change the path to a different Java executable on the command line, and your code is suddenly faster. How amazing that is. That is pretty amazing. There is a question?
Why is it slower at first?
That's a great question. It is slower at first, indeed. So the thing is, Graal Compiler is written in Java. So before you can make use of that code, first it will compile the compiler, right? So it will take a little bit more time to warm up the Graal Compiler and your benchmark with Graal Compiler, but not significantly. And then it will compile the Graal Compiler, it will compile your benchmark, and then will compile your application, and then it will reach the peak performance. But if we're talking about the peak performance, then it's typically higher. It also will use the Java heap for holding its information about the code it compiles. So at some point of time, it can use some parts of the Java heap. Normally, it will compile using the native memory, but with Graal Compiler, it will compile on your heap. So if you want to start the whole heap from the get-go, there might be like a thing that you need to trade off. At the same time, after the compilation, it will give the heap back to you, and you can use your heap fully, which normally doesn't happen with the native memory. So, but if you run Streams API, you are welcome to check. And I'm actually encouraging you to just check and run it with your normal code. If you have performance tests, if you have your favorite benchmark, if you have your favorite Java program that you run, maybe daily, like maybe an IDE written in Java, maybe you can try running that with Graal Compiler and see whether maybe it indexes files faster or something like this. Maybe not, but we'll see. So we tried it also on other languages and other benchmarks. So if you work in Scala, for example, Scala C is the program written in Scala. So we run that and compile different projects from the Scala ecosystem, non-trivial projects. The Scala compiler itself, Akka, Shapeless. On the community edition, you get something like 10, 8, 12% performance boost over normal Scala and normal hotspot. With the enterprise edition, you get the performance boost around 35, 30%, which is ridiculous. That's 1/3 of the time. It's 1/3 faster than hotspot, which is great. So if you run Scala programs, you should check into this, because especially if you run them in the cloud. Because what you can do, you can run it faster in the cloud, use less hardware, and pay a little bit less money to the cloud provider, which is great. So now there has to be an understanding here. There are two implementations of Java virtual machines. There is GraalVM thing that tries to be a virtual machine for everything, and there is an OpenJDK, which is the reference implementation of Java. And they are separate projects. They're both open source projects, and they are both friendly open source projects, but they have different vision, and they have different priorities. So OpenJDK has to be this mature, stable, normal implementation of the JVM, right? It has millions of people depending on it, running their workloads, their businesses relying on that. They need to value backward compatibility. They need to value stability, all that. And GraalVM is a different project that can be different. Well, it's different. So GraalVM takes the virtual machine implementation from OpenJDK, right? So when you run Java from the GraalVM distribution, it actually runs normal JVM. It runs normal JVM garbage collector. It runs the code that does thread scheduling and code caches and everything. It just supplies a different compiler. But normal things in the JVM, they are taken from the OpenJDK project, because it's an open source project, and you can take that. So when OpenJDK also takes the Graal Compiler, a version of that, a snapshot of the Graal Compiler, the open source version, and puts it into OpenJDK distribution. So if you have Java 10 or 11 or further, there is a version of Graal Compiler bundled with that, because the compiler is an open source thing, and they can do that. So it's an experimental compiler, and you can use it and run your normal Java 11 with the Graal compiler enabled by just using command line flags. You just unlock experimental VM options and say that you want to use JVM CI compiler, and boom, your code is running with Graal, and can be faster sometimes. Not always, and it's an experimental option, so you have to understand that. But you can enable that and test that. So at this Oracle Code 1, there was a keynote, and they talked about what's coming in the future of Java. And they talked about value types, Valhalla, Project Valhalla. Right? It will allow you to pack data closely in memory and then thus remove the overhead for objects, and it will make certain programs faster. And they showed the benchmark multiplying complex numbers. And indeed, that benchmark, the performance of that benefited from the prototypes of Valhalla tenfold. I think it was 10 times increase with value types, which will come somewhere in the future. So what we did, we ran this benchmark naturally with Graal, because this is what I do daily. Like I find the benchmark, and I run it on normal JVM, and I run it with Graal enabled, and I run it on the GraalVM, and happily look at the numbers, typically. If the numbers are not happy, then I talk to our compiler team. And they are happy as well, because we like to make it the fastest JVM. The GraalVM has to be the fastest runtime for all languages, right? It has to be fastest JavaScript runtime, it has to be the fastest Java runtime, it has to be the fastest Ruby runtime, and so on. I want it to be the default virtual machine to run programs in all languages, whatever language that is. So we ran this benchmark, and here we time the per operation, and lower is better. And we run this on JDK 11, and JDK 11 with Graal enabled, and then I ran it also on GraalVM RC8. And you can see that very surprisingly, just enabling Graal with 2 command line flags can give you today 2 times performance boost on this benchmark. Why? Because here in the inner loop, we don't have to allocate all those complex objects, because we have this amazing escape analysis optimization, right? So we don't allocate that many objects. We lower the garbage collector pressure. We don't do as much work for doing that. And from that, you get an amazing performance boost. So if you ever allocate objects in your application, if you type new or use something that does new, then maybe you will benefit from using Graal significantly, maybe less significantly. You have to check. But the numbers just show that it's unreasonable not to check, right? Because you might get a great performance boost.
Can you explain that error code?
Yes. It's very high because I run this number. Those numbers come from this poor laptop that I run for 2 minutes, I think, the benchmarks. Maybe if I would run it longer, the numbers would be different, or the error would be lower. It should be lower with a longer benchmark run. But I just did it for a couple of minutes on this, not particularly the most appropriate machine for rigorous benchmarking. When we do actual benchmarking, we use proper server farms and proper hardware and report that properly. But for this particular one, I just ran it on this one. So Twitter is one company that uses Graal Compiler for running their Scala microservices. And Chris Tallinger goes and has talks at conferences about how they use Graal Compiler and what benefits they see and how they save money on the cloud, and talks about the gotchas and what you have to know when you start evaluating Graal, kind of like allowing a longer warm-up and the heap compilation process. So you're welcome to check that out, but I think they get something like 8% performance boost on using the Community Edition compiler. If they tweak that using parameters, they get more. I think maybe 15% user CPU reduction time, which on the Twitter scale, that's a lot of money. And they see, I think something like 5% less garbage collection cycles, which is also amazing. So you're welcome to check that, but let's move further. Let's move further and a little bit more energetic. I have no idea how much time I have. So let's talk about Polyglot. Let's talk about Polyglot, we would like to run different programs, right? Why? Because there are so many programs written in so many languages. Literally, if you look at the NPM, the JavaScript repository for modules, there are over almost 500,000 packages, right? So you can find whatever code that you need to write, that somebody has written that already and put that on the NPM. So all you need to do is just use that. You can do that with GraalVM's JavaScript implementation called GraalJS. But since we are talking about Java programs first, I want to show you how you can use other languages in a polyglot manner to enhance your Java application, right? Because that's probably will be the most interesting for people here. So I have here my normal Spring Boot application. It's a Spring application. Who here writes web applications? Uses Spring? Excellent, almost universally. That's great. Spring is a great framework. So I have my Spring Boot application, and I would like to enhance that and make it use R code to do some computation. And this computation I will put in an R file. So this is how R code looks like, if you haven't seen that before. So it's a function, and defines a function, and takes data, and it plots a thing using the ggplot package, which is a default plotting package for in the R ecosystem. And it plots that data, and it returns an SVG image description, like a string describing an image. So to use this code in my application, I need to create a GraalVM context, and I create that by using the API from the Graal SDK jar. So what I did, I just put that jar on my system path here. So when I run this on GraalVM, it will be added automatically to the class path. But here for the Maven thing to compile things, I need to describe it that the classes are in there. And now I can use and create the context. And the context is where you evaluate snippets of other languages or files. And then in that context, I will just create a source file just by consuming the content out of that R file, class path plot R. And then I will evaluate that source. And since I know that this source just declares a single function, I will just get the result of that evaluation as a function. And if you're wondering, this is a normal function from the Java util function interface. So you can interop, and it makes the best effort to actually do a reasonable thing. There are classes like value to represent a value in the polyglot context. Could be a JavaScript object or could be a Python object. And you can convert them back and forth. But you don't need to serialize because the things between the different languages, because they all operate using the same protocols for the accessing underlying data. You can also even mimic whatever data layout that you want and create a proxy for a certain object. So you can have a JavaScript object that is actually backed by a network buffer. So you, for example, can access points in that network buffer very efficiently without copying, speeding up your network access from JavaScript quite a bit. But here we get just a normal function, and we return it as a bean, and we auto-wire that into this plot function like field. Don't use the field injection. That's not the best practice, but it will do. Also, don't make your beans of the type function data holder string. That's also not probably the best industrial practice. But what you see here is that this plot function is a normal Java object, and you use that as a normal Java object. You can synchronize on that. You can apply that function to whatever Java object that you have. This is a normal data class. Just I wanted to show how it works. And now we can run this as a normal Java application. Run Spring application. It runs on GraalVM. I hope it will run a little bit faster. But it will start here, and it will run it. And it will create those beans and wire it all together. And then it will evaluate that piece of R code, and it will use that piece of R code from normal Java class. So when we'll open this load page, and it will set refresh header for 1, it will repeatedly query this page, and it will repeatedly add new data to the plot. So hopefully we'll see a moving plot, a graph. So our application started. Let's see if it works. Localhost 8080 load. A moving picture. Go. 3, 2, 1, go. Yes. This is a plot written by ggplot, an R package, inside our Spring application. You can use Python instead of that. You can use JavaScript. You can use whatever language that actually solves your problem in the best way, and use that in your Java application. Or you can use that in a JavaScript application. Or you can use that from Python, or from native code. Or you can use native code in the same way, using the same API. You can use whatever you want, and you run it in whatever environment you want. This is fantastic. Yes. Significant. Fantastic. Let's not look at that anymore. You can see it logs also, the R code uses the Spring logging to log to our Java log file normally, which is great because you can unify things like logging, application configuration across different languages, and it's quite fantastic. Next time you hear that Marvel has the most ambitious crossover in history, remember that this Spring Bean is an R function, which is way better. OK, let's come back. If we talk about other language implementations, JavaScript. It's fast, it's efficient, it's compatible with the ecosystem. It's compatible to the level of normal node implementation in browsers. If you want, this is the candidates table where the JavaScript community records the compatibility. If you're wondering, JJS and JJS 10 are an Nashorn. Not very compatible, because it's harder to maintain the compatibility when you have to do bytecode transformations and generation out of the language. And we just need to create an interpreter, which is way easier. It's also quite fast. If you ever ran JavaScript on the JVM, typically it's not very fast. GraalVM Community Edition composite score is about 4 times faster. The Enterprise Edition is about 6 times faster than Nashorn on a given set of benchmarks. So you should try. I know that some people have tried. And Vertex uses some GraalJS implementation. And maybe you can find a person talking about that. Maybe Paula. And see how it goes. You can use GraalJS modules on the stock JDK 11. You just need a bunch of dependencies, and you just need a bunch of common flags to enable the JVM compiler, and it will run fast on the JDK 11 as well. Stock JDK 11 with just a bunch of jar files. This is one of the benefits and cool things about writing Java applications. You can distribute them as jar files. Fantastic. Ruby is fast. R is fast. Python is the youngest and not very compatible yet with the ecosystem, but it will be fast. And we are concentrating on making NumPy and SciPy workloads work. So we want to make sure that our Python implementation supports the normal machine learning work use cases, because Python is probably what's used for machine learning the most. But it's not there yet. It can evaluate snippets of Python, but not. Another benefit is that since our languages are virtualized, right, they work in the interpreters, we can connect tools through GraalVM, and they will work across all the languages. If anyone is interested, I can show you a demo, but not right now because I saw a time, 5 minutes left, where we will debug our code using normal Chrome debugger as you would debug JavaScript code. So you can use tools for your Polyglot applications normally. You can use the heap viewer, the visual VM. You can use the CPU sampler for profiling the Polyglot applications normally, universally, without regard of any language. Now, we have 2 minutes, and we'll have to be really, really fast. Since everyone uses Spring, I want to show you a Spring application here. Let's count. I will show you how fast it starts with GraalVM. You said the startup is a little bit slower in GraalVM. So I have this compiled Spring application here. Whoa, what happened? No, back. Oh, no, yeah, this is fine. This is fine. I will start it, and I want you to count to see how slow it starts, right? So I will do 1, 2, 3, and then we'll do 1, 2, 3 further to see how many seconds it takes to start the Spring application, right? So let's do 1, 2, 3. No. It started in 400 milliseconds. That's too slow. That's too slow. Let's try it again. See, 40 milliseconds. This is better. It starts in 40 milliseconds. It starts even faster on a more powerful machine. Why? Because we compiled this Spring application ahead of time to a native image. We got really fast, incredible startup. And we got lower memory overhead. Unfortunately, it doesn't work for all applications. There are a bunch of things that limit what we currently do. in a nutshell, it does a static analysis what classes are used, and then it compiles that to machine code ahead of time. And then it wraps it into the binary for the operating system to be able to run it, right? And the startup of this thing is incredible, milliseconds. If you do command line tools or anything that requires fast startup, like you run serverless environment or you run microservices where you want to have your startup as fast as possible, you should check it out. What I know, I will skip this. There is an example that node.js runs really, really fast. Scala C runs really, really fast. I mean, it starts really, really fast, which is impressive because normally people don't think that Scala compiler is really fast. It doesn't yet work for out-of-the-box Spring applications, but we are working on that. By we, I mean the Spring team and the GraalVM team. And we are making sure that in the future it will work on JDK 11 and on Windows as well. So currently Linux, Mac OS. And the next slot in the same room, if you're interested in that, Paulo Lopez will talk about building native images. And he will talk in more details about that. But since we're out of time, I will not make more information about that. So it's a high-performance polyglot language level virtualization embeddable across the stack. So now here I would talk to you about how you can run JavaScript functions in a database, if you would like. And you can download experimental builds of Oracle database. You can run it. There are instructions how to do that. You can put modules from NPM into your database and call them as user-defined functions. So you don't have to write PL SQL for your complicated data processing logic. But you can use code that somebody else wrote or you wrote using JavaScript if you feel yourself more comfortable writing JavaScript. I know I do because I'm very bad at PL SQL. But if you are good at PL SQL, you should continue using that because it's a great language. And if you're proficient and comfortable with it, it's very efficient. It's highly optimized. It has a history of 40 years. It's good. But if not, maybe you should look into this. There is a thing called Vertol Apex where you can write the full application, web application, inside the database in JavaScript or Python, powered by GraalVM. I think they released that recently in a demo or something, and you can read about that and you can try it. I'm not sure what's the exact use case for that. But we have to understand that not everyone is a proficient web application developer. So maybe some people are, you're laughing, but like I'm sure there are use cases for that. The team of GraalVM team is quite large. There are many people working on this, and they are very incredibly brilliant people. So thanks to them. But we have to understand that building a virtual machine is a hard work and it's a community effort. So what I want to encourage you to do is to check it out, go through the website, maybe look at the Getting Started guide, maybe download it, maybe run it on your workloads. It can be a drop-in replacement for Java apps. It can speed up your Scala execution times. It can compile some things for faster startup. Not all of them, but some of them. And I would like you to come back to us with any feedback that you have. We are still not at the 1.0 release, and we still have time to fix anything major before 1.0 is released. So that would be great if you send us any feedback. There is a mailing list that you can join the discussions. There is a Twitter handle where you can ask questions. For questions about life in general, maybe my personal handle is better. But anything GraalVM related are welcome there. We are trying to look at that and respond and be friendly in the community. Go through the code on the GitHub. It's Java. You should be proficient with that. It's a very good project, and it's very exciting. So personally, I hope that it will take on more and more in the future. And this is it. Join building a universal virtual machine. Thank you.